Catalysis. You all know what is a catalyst and what is catalysis. Catalysis was first employed by Berzelius in 1836 to identify a new entity capable of promoting the occurrence of chemical reaction by a catalytic contact. Catalyst was seen as something that is added to the reaction to speed up the rate of reaction. That is catalytic force, without being consumed or produced in the process. Catalysis plays a key role in the production of chemicals and materials. This is the energy diagram for a generic reaction and the effects of catalyst on the reaction profile. In this case, the dotted lines, this one, and this is the product formed. Dotted line represent the uncatalyzed reaction. The solid thick line, this one. Solid thick line represent the catalyzed reaction leading to the same product. And the solid thin line, this one, represent catalyzed reaction leading to different products. The difference in energies, that is this one indicated by arrows. The difference in energies indicated by arrows represent the activation energy barrier, that is delta A for the forward reaction and enthalpy of the reaction delta H. Catalysis is mainly of two types: homogeneous catalysis and heterogeneous catalysis. First one is the homogeneous catalysis. Homogeneous catalysis refers to a catalytic system in which the substrates for a reaction and the catalyst components are brought together in one phase, most often the liquid phase. The example is this one, that is A aqueous plus D aqueous in presence of catalyst, that is C aqueous, gives F aqueous. Next is heterogeneous catalysis. A catalyst in a different phase to the reactants represent heterogeneous catalysis. Example, gaseous reactant passed over solid catalyst, that is A gas react with B gas in the presence of solid catalyst to form D gas. Heterogeneous catalysis, mechanism and theory. A gaseous reaction taking place on the surface of a solid catalyst proceed via the following steps. First is the diffusion of reactants to the surface. That is, the reactants diffuse to the surface of the catalysis. In this process, the reactants first get in contact with the external surface, out of which some of them cross the barrier and enter the interior exposed surface. That includes paths and cracks on the external surface. Next is the adsorption of reactants to the surface. That is, the molecules then get adhered to the suitable sites available for adsorption. Third one is chemical reaction at the surface. The reactants when bound to the surface have a higher probability of reacting with each other, and after the reaction they form an intermediate compound, that is the chemical reaction. Next one is the desorption of products from the surface. After chemical reaction, the intermediate compound gets desorbed from the surface, which again becomes available for adsorption for other molecules to come. Last one is diffusion of products from the surface. That is, the intermediate compound disintegrates to form the final products, which then diffuse out of the internal pores and the external surface of the catalysis. In this case, the rate determining step is the chemical reaction, that is the third one, occurring at the surface. Chemisorption plays an important role in heterogeneous catalysis. Langmuir-Hinshelwood mechanism. First is unimolecular surface reaction. This involves chemical reaction between the reactant A and a vacant site S on the surface. The elementary process of the reactions are: first is the formation of AS. It is a reversible reaction. That is, AS decomposes to form A pluses also. That is, adsorption and desorption are taking place. And finally, AS decomposes to form products. That is the decomposition reaction. According to Langmuir-Hinshelwood hypothesis, the reaction rate, the rate of the reaction may be represented as R equal to K2 into theta, where theta denotes the fraction on the surface covered. If we assume a steady state with respect to the concentration of S, then dAs by dt equal to 0. That is equal to K1 concentration of A into concentration of S minus K inverse on concentration of AS minus K2 into concentration of AS, where concentration of S represent the vacant sites on the surface. That is equal to the total concentration of surface sites multiplied by the fraction of the sites which remained uncovered. That is, concentration of S is equal to Cs into 1 minus theta. From equation 2, concentration of AS is equal to K1 into concentration of A into concentration of S divided by K inverse 1 plus K2. The concentration of AS on the surface is given by AS is equal to Cs into theta. And Cs into theta can be represented as Cs theta is equal to K1 into A into Cs into 1 minus theta divided by K inverse 1 plus K2, or 1 minus theta by theta equal to K inverse 1 plus K2 divided by K1 into A, or 1 by theta minus 1 is equal to K inverse 1 plus K2 divided by K1 into A, or 1 by theta is equal to K inverse 1 plus K2 divided by K1 into A plus 1. That is equal to K1 into concentration of A plus K inverse 1 plus K2 divided by K1 into concentration of A. Theta equal to K1 into concentration of A divided by K1 into concentration of A plus K inverse 1 plus K2. Substituting the value of theta in equation 1, we get R is equal to K1 K2 concentration of A divided by K1 into concentration of A plus K inverse 1 plus K2. Therefore, equation 3 may be written in the form 1 by R is equal to 1 by K2 plus K inverse 1 plus K2 divided by K1 K2 into concentration of A. According to equation 10, a plot of 1 by R versus 1 by A would give a straight line with intercept equal to 1 by K2 and slope equal to K inverse 1 plus K2 divided by K1 K2. For gaseous adsorbates, the concentration is expressed in terms of partial pressure. Thus, equation 9 and 10 can be written as R equal to K1 K2 into PA divided by K1 into PA plus K inverse 1 plus K2, or 1 by R is equal to 1 by K2 plus K inverse 1 plus K2 divided by K1 K2 PA. Let us consider the two cases. First is the case 1. If the rate of decomposition is very large in comparison with rate of adsorption, that is, K2 is found to be very much larger than that of K1 into A plus K inverse 1. In this case, equation 9 reduces to R equal to K1 into A. That is, the reaction is first order with respect to A. Consider the second case. If the rate of decomposition is very small compared with the rate of adsorption and desorption, then K2 is found to be very much smaller than K1 into A plus K inverse 1. Then equation 9 becomes as R equal to K1 into K2 into concentration of A divided by K1 into concentration of A plus K inverse 1. That is equal to K2 K into concentration of A divided by K1 into concentration of A plus 1. That is also equal to K2 K dash PA divided by K dash PA plus 1, where K or K dash is equal to K1 by K inverse 1. It is the adsorption equilibrium constant. Two situations arise depending upon pressure. At low pressure, when the reactant is slightly adsorbed on the surface, then theta tend to 0, K dash in PA is found to be very much lesser than 1, so that R equal to K2 K dash PA, that is equal to K into PA. That is, the reaction is first order with respect to A. Here K equal to K2 into K dash. Thus R equal to minus dPA by dt, that is equal to K into PA, or PA is equal to PA star exponential minus KT. This means that the partial pressure of the gas decreases exponentially with time. At high pressure, when the reactant is strongly adsorbed on the surface, theta tend to 1 and K dash into PA is found to be very much greater than 1, so that R equal to K2. That is, the reaction is 0 order with respect to A. Thus, we can write R equal to minus dPA by dt, that is equal to K2. That is a constant which can be integrated to give PA equal to PA0 minus K2 into T. This means that the partial pressure of the gas decreases linearly with time. This figure represents the pressure dependence of the rate of a unimolecular surface reaction. That is, the variation of reaction rate against pressure is shown in figure. Bimolecular surface reactions. A bimolecular surface reaction may involve a reaction between two molecules A and B on a surface. The Langmuir-Hinshelwood mechanism assumes that the two molecules are absorbed on neighboring sites on the surface of the catalyst. That is, A plus S gives AS, that is a reversible reaction. B plus S gives BS, that is also a reversible reaction. And finally, AS react with BS to form S and product, where S is the vacant site on the surface. The rate of the reaction is given by R equal to K3 into concentration of AS into concentration of BS. That is equal to K3 into theta A, theta B, where theta A and theta B are the fractions of the surface sites covered by A and B respectively. Assuming steady state approximation for AS and BS, we have dAs by dt is equal to K1 into A into S minus K inverse 1 into AS minus K3 into concentration of AS into concentration of BS, that is equal to 0. dBs by dt is equal to K2 into concentration of B into concentration of S minus K inverse 2 into BS minus K3 into AS into BS, that is equal to 0. Where S is the concentration of vacant sites on the surface. The fraction of the vacant sites theta v is given by theta v is equal to 1 minus theta a plus theta b. If Cs is the total concentration of the sites on the surface, then concentration of S is equal to Cs into 1 minus theta a minus theta b, that is equal to Cs into theta b. Also, concentration of AS is equal to Cs into theta a. Concentration of BS is equal to Cs into theta b. Using these expressions, equations 2 and 3 becomes K1 into A into Cs into theta v minus K inverse 1 Cs into theta a minus K3 into Cs square theta a theta b equal to 0. K2 into B into Cs into theta b minus K inverse 2 Cs theta b minus K3 Cs square theta a theta b equal to 0. Equations 7 and 8 can be solved to yield theta a and theta b. Consider a case when K3 is very small, so that equations 2 and 3 become K1 into A into theta v minus K inverse 1 into theta a equal to 0. K2 into B into theta v minus K inverse 2 into theta b equal to 0. Here the common factor Cs cancels out. Rearranging equations 4 and 5, we get theta a equal to K1 by K inverse 1 A into theta v, that is equal to K1 into concentration of A into theta v. Theta b is equal to K2 by K inverse 2 into B into theta V. That is equal to K2 into concentration of B into theta V. Where K1 equal to K1 by K inverse 1 and K2 equal to K2 by K inverse 2. Substituting for theta A and theta B in equation 4, we get theta B is equal to 1 minus K1 concentration of A theta B minus K2 concentration of B theta B. This equation can be rearranged to give, that is, theta V is equal to 1 minus, this theta V is a common term, so taking outside, theta V into bracket K1A plus K2B dividing by theta V. Theta V by theta V is 1, that is 1 minus 1 by theta V minus K1 concentration of A plus K2 concentration of B. 1 by theta V is equal to 1 plus K1A plus K2B. Therefore, theta V is equal to 1 by K1A plus K2B plus 1. Substituting for theta V in equations 11 and 12, we obtain theta A is equal to K1 into A divided by K1A plus K2B plus 1. Whereas theta B is equal to K2B divided by K1A plus K2B plus 1. Substituting for theta A and theta B in equation 1, the rate of reaction becomes R equal to K3, K1, K2. Concentration of A into concentration of B divided by 1 plus K1 into concentration of A plus K2 into concentration of B the whole square. Expressing concentrations in terms of partial pressures, the rate of the reaction becomes R equal to K3, K1, K2 into PA, PB divided by 1 plus K1 PA plus K2 PB the whole square. That is equal to K dash into PA PB divided by 1 plus K1 PA into K2 PB the whole square. Whereas K dash is equal to K3 K1 into K2. Consider the first case. When A and B are both weakly adsorbed. In this case, K1 into PA is found to be very much lesser than 1 and K2 into PB is also lesser than 1. So that equation 13 becomes as rate of the reaction R is equal to K dash into PA PB. That is, the reaction is first order with respect to A, first order with respect to B, and overall the reaction is second order. In case 2, when A is adsorbed more strongly than B. In this case, K1 PA is found to be very much greater than that of K2 PB. So that equation 18 becomes as R equal to K dash into PA PB divided by 1 plus K1 PA the whole square. That is, the reaction is first order with respect to B. That is the weakly adsorbed component. Consider the case 3. When one reactant is very strongly adsorbed, let A be the very strongly adsorbed component. Then K1 into PA is found to be very much larger than K2 into PB, and K1 PA is found to be very much larger than 1. Then equation 18 becomes R equal to K dash PA PB divided by K1 square into PA square, that is equal to K3 into PB by PA, where K3 equal to K dash by K1 square, that is equal to K3 K2 divided by K1. The rate of the reaction is inversely proportional to the concentration of the very strongly adsorbed component. That is, the reaction is inhibited by such a component. Example is reaction between hydrogen and oxygen on platinum.